Good afternoon, ladies and gentlemen, and welcome to the KwaZulu Natal Centre's webinar today. We will be discussing greenhouse-free solutions for sustainable power. Before we start, a few webinar considerations. Attendees are reminded to ensure the volume is turned up on their device. Ensure you have a stable internet connection. This will ensure the streaming and audio will run smoothly. Attendees can ask questions via the questions panel located within the GoToWebinar control panel, and by default, it's located on the right-hand side of your screen. The chat function is reserved for webinar organizers and panelists to communicate with attendees. Attendees will not be able to chat with each other. However, we encourage you to ask questions. A recording of this webinar will be made available on the SAIEE YouTube channel, the SAIEE TV, under the KZN Centre playlist. You will see in the chat function there's links to the SAIEE TV channel. We encourage you to subscribe. It is free. A certificate of attendance will be issued a few days after this webinar. I would like to introduce you now to our host today, Mr. Shepard Nkosi, who is the chairman of the SAIEE Kwa-Zulu Natal Centre. He holds a Bachelor of Technology degree in Electrical Engineering, a post-degree with USQ, University of Southern Queensland, Australia, a post-degree in Project Management with the University of Stellenbosch, and is currently completing his Master's degree, MSc, with KZN. As I mentioned, he is a chairperson of the SAIEE Kwa-Zulu Natal Centre, and he served as Vice President of the Durban University of Technology Advisory Board and is professionally registered with EXA. Over to you, Shepard.
Thank you, Ms. Afrobos, and thank you to all that are connected this afternoon. Warm welcome to one and all. As the theme is indicated or mentioned this afternoon, we'll be discussing the greenhouse-free solution for sustainable power. I know energy security is a concern for all of us, more in particular in our country, South Africa. We're going through quite a number of challenges. Included in those is the load shedding that we are currently going through. We have our keynote speaker this afternoon, Dr. Dick Helbig. Dr. Helbig is responsible for serving people and society and achieving Siemens Energy goal to become the most valued energy technology and company globally by energizing our planet without CO2 emissions. He is motivated and inspired by joining sustainable developments based on responsibility, trust, and teamwork that make a better world, achieving the UN development goal. We have Dr. Helbig, as I've mentioned, as our keynote speaker this afternoon. Dr. Helbig, we look forward to your presentation. Over to you.
Thank you, Shepard. Thank you, Ming. I will share my screen. You should be able to see my screen and also the cursor. Is that right?
Yes, it is.
Okay, perfect. Yes, good afternoon from Germany, and thank you very much for inviting me to give you that presentation. It's very close to my heart. It's about sustainability, it's about our future, and it's especially on actions we have to do on our power grids. So the title is Greenhouse Gas-Free High Voltage Switchgear for Sustainable Power Grids of the Future. I structured the webinar in 5 parts. The first one is, why do we have to change technology as it is today? How the technologies look like, switching and insulation technologies. The what, how the products and systems look like. The fourth point is what regulations are available globally and what does that mean also for the evaluation and choice of switchgear? And the last part then is a summary and the outlook over the next years. First question, why do we have to change? The United Nations Sustainable Development Goals are actually describing actions, key actions we have to take regarding poverty, inequality, climate change, environmental degradation, peace and justice. And looking on the electrical power grids, they will play a key role into fighting climate change and environmental degradation. So we would like to focus on that, and having now a look on power grid companies, I would give two examples. One example is the transmission grid operator like Eskom, who are globally taking actions to achieve the sustainable development goals. This is the sustainability report of Eskom, the latest one, and you see that the activities are also structured along the different United Nations Sustainable Development Goals. A second example is, or having a closer look on that sustainability report, you see that the greenhouse gas emissions are well documented here, and you see it's according the global framework of structuring the emissions in scope 1, 2, and 3. Most important for us is so-called scope 1. This is the direct emissions which come from Eskom, and you see that the biggest part is the generation part. But now looking on the other parts, it's the motor vehicle part. It's the so-called fugitive emissions and waste disposal. So those are the big points to actually take actions on. On the generation part, it's the shift to renewable power generation through wind, sun, and hydro actually. And now looking on the grid part, you see that there are so-called fugitive emissions. And what are fugitive emissions? Fugitive emissions are described here on the lower right-hand side. This is mainly the release of or leak of sulfur hexafluoride, SF6 gas. As you probably know, SF6 gas is a man-made gas. It's used for switching and insulating an electrical system. It's a standard gas used globally in medium voltage and high voltage. And it is the most potent greenhouse gas in the world. So you see that if a transmission grid operator wants to become CO2 neutral, you have to, in the long term, get rid of SF6. And second example here in the city of Cape Town, from the distribution view, but also from the city view, there's also the action program described here in the so-called strategic focus areas. And looking here on the strategic focus areas, for example, of Cape Town, there is a so-called zero emission buildings and precincts, including the grids, the electrical grids. And you see that on the right-hand side, the goal is also to become net zero carbon by 2030. This is only possible by not to install SF6 anymore, but to install an alternative which make the grid operators be able to become CO2 neutral. So how do we do that? On the left-hand side, you see here the overall sustainable development goals, and looking on electrical power grids from Siemens Energy side, we are completely committed to realize those goals and also enable the power grid operators globally to realize their sustainability goals. So we see three main goals to be achieved. We have to keep good health and well-being. We have to provide affordable and clean energy, and we have to take climate action. So what does that mean for electrical power grids? First of all, whatever we do in the future, instead of SF6, it must have the highest occupational safety for production, operation, and service, and also for the public health and safety. So that means whatever we substitute instead of SF6 must have a zero toxicity and a zero pollution. So certain gases, so-called forever gases, which will stay in the environment forever, PFAS is the shortcut for that, we have to prevent. The second is the affordable and clean energy. That means not only the clean generation must be realized by renewable generation, but we also need the clean grids without any greenhouse gases like SF6. And looking on climate action, again, it goes without SF6 the future, and as an ideal state will be gases and substances with a global warming potential of 0. So this is just an overview which shows the whole complexity of electrical grids with communities, with industry, with generation of either solar or wind, in this case, wind generation. And the target is to have a greenhouse gas-free electrical grid. So just to give some examples, what does it mean, the SF6 installation? And just a few facts regarding SF6. There are 10,000 tons of SF6 installed globally every year, and it's 25,000 times stronger than CO2. It also stays a long time in the atmosphere, 3,200 years. And if you look how many trees you actually need to compensate that, you see that there are 19 billion trees almost needed to absorb the CO2 equivalent of the yearly installations. That's a huge area. It's just described here in soccer fields or in countries or what cars are emitting. So this is installed in CO2 equivalents of SF6 every year. And looking on leakages, depending on the leakage rates, actually, you see that this is still, just on the leakage side, still a huge part of newly planted trees every year to compensate for the SF6 emissions every year. Just to give a few numbers on that. So how to change? What are the options? This is now the characteristics of SF6 here in the first column. You see there are so-called global warming potentials. This is the latest evaluation of the Climate Council in so-called Assessment Report 6, which is the latest one, states that this is the strongest greenhouse gas in the world, and it's 25,000 times stronger than CO2. So as I said, it's in the atmosphere forever. That's actually also the reason why it's such a good switching gas, because it's very stable and you cannot destroy that, actually, not even with electrical energy, nor in the atmosphere. So looking on that, you see the big point is that it has a very high dielectric strength. What we said was 1. It's very stable, so you can hardly take it apart. And you see it here, certain decomposition products, which actually will evolve once you start switching with that. The second column is so-called clean air. So what is clean air? Clean air is the air surrounding us, minus moisture and minus CO2. That's clean air. So it's around 80% nitrogen and 20% oxygen. Clean air is you can buy it everywhere. it's very easy. You can even generate it by filtering machines and so on. It has a very low boiling point, which is a strong point. It has a perfect CO2 equivalent of 0. And you see here on that point, that's the weakness of the clean air, is the dielectric strength. So it's less than 50% of SF6. That has to be compensated by design. I will show how this is done. You see it's also very stable, the air surrounding us. And actually, once you in use, actually, there are no decomposition products decomposition products while switching or so on. In case of failure, there will be ozone, O3, which recombines very fast to O2 again, and NOx also the same, which is kept into the filter material inside. So actually, it's the clean air, or synthetic air, as we also call it. It's the best solution sustainability-wise, which can be used. We did lots of research, more than 500 gases we looked at, and the second best from our perspective are the so-called F-gas mixes based on fluornitrile. You see here, it's also a strong greenhouse gas with 2,700 times stronger than CO2. It has a boiling point of -4, which means that in lower temperature it liquefies. And also it has a lifetime of 30 years. So in order not to liquefy with -10 or -20 or 30 degrees, as it in some parts of the world is common, it's mixed. It's mixed with CO2 and with O2. And then actually you have a mixed global warming potential, and you achieve lower operating temperatures down to -25. And the dielectric strength is then in between clean air and SF6. The biggest disadvantage of those gases is once you start switching with them, it falls apart and it does not recombine entirely. So after switching several times, you will have lots of different decomposition products listed here, and some of them are toxic, and that's the problem to handle it with. So from our perspective, all the alternatives have good and bad things, and there has to be compromises being taken. We decided that the clean air installation has the highest benefits also in operation, and we listed the benefits, which are even better than SF6 today, and also towards the different alternatives. So the global warming potential of 0, and ozone depletion potential of 0. It's completely non-toxic regarding different aspects, also regarding carcinogenity, mutagenity, reprotoxicity. So it's a perfect gas toxicity-wise. It's non-flammable, it's high stable, has a very low boiling point and no liquefaction. It's well known. It has a proven material compatibilities. It doesn't have F-gas in, and therefore lowest requirements for training, transport, installation, operation, reporting, and recycling. It doesn't have C in. So whenever you have C in the gases and you put energy to it, soot is generated, and soot is a conducting substance which we want to prevent. So there is no documentation and reporting duties related to clean air gas. There are no CO2 compensation costs, like in many parts of the world are meanwhile introduced. There's no risk of future tax or compensation. There's no gas recycling requirement. And at the end, actually, you can leave the gas out of the compartment without any additional topics. You just put it through the filter, and then it's out in the air. So there's no recycling, there's no risk of health issues in this environment. So looking now a bit on the history of switching, like more than 100 years ago, the arc interruption was done in oil. You see here the first oil switches here in wooden barrels, actually 120 years ago or 30. And you see here then the first industrial oil breakers you see here. Actually, we did produce them in Berlin in 1910. And the next generation were then the so-called SF6 breakers that began in the 60s. So there was a lifetime SF6 braking technology starting in 64, in 68, 69, the GIS. And that was further developed over the years, as you see here. Now this will be substituted by arc interruption and vacuum. You see here a few pictures. So we did the first installations in 2010 for high voltage for 72.5 kV and 2017 for 145 kV. So this is the heart of a circuit breaker. This is a so-called vacuum interrupter tube, which you see here. So there is a contact system here. The white is ceramics actually, and this is the conductor going from the top to the bottom here. So what are the benefits? First of all, vacuum technology is successful operation in medium voltage for more than 40 years, almost 50 years. It is very reliable. I give you some statistics after that because it's hermetically tight, sealed. It has a very high performance. It's higher than today's SF6 technology. I will give you examples. So it's a higher number of short circuit interruptions possible. It has an excellent rated nominal current and rated short circuit currents over the lifetime. It's perfect for lower temperatures down to -60 degrees Celsius. It doesn't have any maintenance connected, so you switch there up to 10,000 times. And once you achieve that, which is very seldom to switch 10,000 times, you exchange it completely. So no maintenance needed, and there are no CO2 emissions connected to that vacuum interrupter. Just to have a look inside for those of you who do not haven't seen inside a vacuum interrupter, here's the current conductors are from 1 to 8. So this is the contact system here in 4. So 4 is a movable contact which can be moved downwards, and that's the current is flowing this way, and outside you see here the ceramics in there. So looking on the inside, once you start switching, you see that on the right-hand side, we do have simulation programs, how the magnetic field is actually working in the contact system. And you see that it's very important that to achieve a so-called diffuse arc mode. That means that the energy is flowing and completely spreading over the whole area which you see here. So this is a perfect vacuum interrupter switch which you see here, and that's what we developed over the years based on the medium voltage technology further into the high voltage technologies. Another big benefit of the vacuum interrupting technology you see here. Horizontally, you see the braking current up to 100 kA, and vertically, you need the arc energy which is generated during switching. And you see, let's have a look on for example, 40 kA. You see that an oil breaker had around 800 kWs generated in the past. SF6 had about 50% of that, and you see that a vacuum interrupter has around up to again times 10 lower arc energy generated. Why is that so? That has 4 reasons. There is a low arc voltage, there is a low arc length, there is a very short arc time, and overall you get a very low energy. What does that mean if you have low energy in? You have low wear in there, so the contact systems are not as stressed as an SF6 one or oil one, and you need less energy to shift to switch. And needing less energy, the whole system is less stressed. So that's the reason why the vacuum interrupter is so strong, and why the vacuum interrupter medium voltage is the clear leading technology, and for high voltage will become the leading technology. Just giving you a few pictures of existing products. So on the left-hand side, you see here a medium voltage vacuum interrupter for 15 kV and 50 kA. So the length a bit and the number of porcelains indicates the voltage, and the diameter here of the metal part used here is indicating the short circuit current capabilities. You see that next to it then, the first 100 kA vacuum interrupter for medium voltage was type tested 7 years ago. And now you see the steps forward to high voltage. This is a 145 kV vacuum interrupter for 40 kA and 3150 amps. And on the right-hand side, you see a vacuum interrupter for 245 kV, 63 kA, and 4000 amps, which is in development right now. So how does the global community look on the next generation of circuit breakers? There is a so-called green book available from SAIEE, which are so-called flagship publications, and it indicates the technology past and the technology future. So the first line here is indicating the air blast breakers around the 50s to the 80s. The vacuum interrupter starting in the 70s for medium voltage, and here it states the future depends on the high voltage availability. I will show you that it is available today already. The SF6 shows here the history of SF6 from the 60s and 70s, and they show an unsecure future due to legal regulation. And let's make it clear, SF6 will disappear in electrical grids. SF6 is not needed for electrical grids. Here are the so-called alternative gas circuit breakers. Those are the fluoronitrous ones, which are 10, 15 years old. And it states here that the experts don't see a future due to reliability and handling issues. We share that view. This is also our opinion. The latest technology, or the lowest line here, is the so-called semiconductor high HVDC circuit breaker, which started a few decades ago. And the problems right now is that the semiconductor technology has very high losses. That's why, from our perspective, the semiconductor high voltage circuit breakers will not be realized within the next 30, 40, 50 years. So looking on all the technologies, the vacuum circuit breaker technologies, from our perspective, is the future. So how is it produced? This is an overview, which indicates you that you need a very, very high quality production to produce a vacuum interrupter. It needs good surface treatment, a clean room assembly. It then has to be brazed together, glued together in a ultra high vacuum oven, and it needs a vacuum sealing brace. So give a bit more details here. You see you have an input how that is produced. So the parts are cleaned first of all and then assembled. In the next part, it's actually put in a one-shot brazing technology under clean room production. You see that looks more like a chip production for a computer than a production of a high voltage product. But this is the production of the vacuum interrupter. After it's produced, there is a very thorough check of the quality, also an X-ray check here, and electrical checks and mechanical checks, and that actually leads to a very high quality. Looking on the history of vacuum interrupters, you see the medium voltage starting on the left, and then in the 2000s around, it became a high voltage vacuum interrupter for 72.5 kV and for 145 kV. You see here the 72.5 kV. I don't know if you have it in my camera here, but it's also standing behind me. So this is a 72.5 kV vacuum interrupter, which is here inside the this live tank vacuum and circuit breaker, or inside that GIS here. And on the right hand side, you see the 145 kV vacuum interrupter, which goes into the live tank technology and into the GIS technology. So this is the way forward, and you see that there are more than 5 million vacuum interrupters produced. We do produce them on the same production, with the same production technology as medium voltage. So we have a very high reliability on that. Looking on reliability, I just want to give you a few numbers. A vacuum interrupter produced has a so-called mean time to failure of 68,000 years. Just to compare what SF6 technology achieves. So our SF6 breakers have a mean time between failure of 6,000 years, so which is 10 times lower. But looking on the SAIEE average globally, according to SAIEE statistics globally, the mean time between failure of a circuit breaker has 300 years. So you see that statistically, the reliability of vacuum interrupters is very high, also compared to gas interrupters. This is a kind of summary. So what we need to solve is we need new installation technology, and we need new switching technologies. On the lower left-hand side, you see the different technologies in different colors. It's an orange SF6, and blue is air insulation, and black is CO2 insulation, and green is fluornitrile insulation, and red is fluorketon insulation, which is a different F-gas also. And you see, looking on installation performance, safety, reliability, long-term stability, low environmental impact, and health impact, there are plus and minus for everyone. So from our perspective, the blue one is the best overall solution, although it has the lowest installation performance. On the right-hand side, you see the same for switching technologies, and again, you see the different colors, switching and SF6, switching with vacuum in blue, and black CO2 switching, green is fluornitrile switching, and red is fluorketon switching. Here, from our perspective, it's very clear that the vacuum interrupter technology is the strongest switching technology, also compared to SF6. Another summary of the three technologies, vacuum, clean air, SF6, and F-gas, is shown here. Different aspects of health, safety, and environment, operational performance, maintenance, and reporting. There are plus and minus all over, but the highest benefits is the combination of vacuum and clean air technology. So how do different manufacturers globally now see the future? Where do they go for? Here are three official statements, open letters of manufacturers. On the left-hand side, it's a joint statement of equipment manufacturers, which state that they see the future free of fluorinated gases, means without SF6 or other F-gases, so with clean air or other natural gases. You see here it's 10 different manufacturers here. In the middle, you see two more. Those are the instrument transformers manufacturers, Trench and Pfiffner. And on the right-hand side, you see the press release of Siemens Energy, who state here that Siemens Energy goes for vacuum and clean air technology, so greenhouse gas free technology, and the aim is to sell only F-gas free high voltage switching technology starting in 2030. This is in 8 years. So we are in the middle of the transformation of the SF6 portfolio into the greenhouse gas free portfolio. To realize that, Siemens Energy is building a new factory for high voltage vacuum interrupters in Berlin. It started last year, and it will go into operations in 2023, next year. To give another overview about different offerings available The first line is the medium voltage offerings. You see here on the left-hand side, there are two offerings with F-gases. And on the right-hand side, you see that there are plenty of offerings for F-gas-free components. So it's either with O2, N2, or CO2, or mixtures of that. So there's a wide variety of offerings. The second line gives the overview about high voltage, including switching. You see on the left-hand side the solutions available with F-gases, with C4 or C5. And on the right-hand side, you see the whole variety of different offerings from different companies for natural origin gases without F-gas. And on the last line, actually, those are the offerings without switching capabilities, like instrument transformers, for example, or lines. And you see also there are several there's the whole variety of offerings here regarding that technology here. So we see the clear future in greenhouse gas-free technology based on natural gases, and the variety of offerings is very big on that part already. Now, to have more details into the portfolio of Siemens Energy, just to give an overview. First, since 2010, so since 12 years, we do have the 72.5 kV live tank in operation. Right next to us is the big brother, 145 kV live tank, which is developed and in operation. Next to it, you see the 72.5 kV GIS, which is very more than 1,000 times ordered meanwhile, and more than 200 are in operation. Right next to it, you see the big brother of the 72, so that's the 145 kV GIS. And on the lower left-hand side, you see the dead tank solution for 145 kV, which is very common in the United States and also in China. Next to it, you see a 420 kV so-called bus duct here, which doesn't use any SF6 anymore, just clean air. And next to it, you see the voltage and current transformers up to 420 kV with clean air insulation. And next to it, you see the so-called station service voltage transformers, which are also available up to 420 kV. Just to give an overview of some products, this is the 145 kV live tank circuit breaker. So from the outside, you don't see a difference to the SF6 technology. So in here is the vacuum interrupter up here, and it's surrounded by clean air. So from the outside, it's hard to see. You see it a bit, the diameter here on the upper insulator is a bit bigger than on the lower one because the vacuum interrupter is in here, but that's the only way to see it. Looking on the different capabilities here on the technical data, if you look on the right two columns, you see on the right column, you see a classical SF6 breaker, 145 kV, with the capabilities of short circuit breaking currents, of number of operations, of rated break time, and the different characteristics and technical data down here. And next to it, you see the 145 kV vacuum interrupter and clean air technology. And you see here very clearly that is superior to SF6 technology in the number of operations at rated short circuits. It has higher number of operations for the rated continuous current, so from 6,000 to 10,000. Most of the different data are identical then, what the current is concerned, what the short circuit is concerned, and so on. And going to the lower side, you see that it has a better performance in lower temperature, so it doesn't need any heatings or mixed gases like other SF6 technologies, because SF6 liquefies usually at -25. And you see also then, especially on maintenance schedules, there is less maintenance related to the new technology than to the old. So the checks don't have to be at 6,000 after 6,000 operations, but after 10,000 operations. What's most important, what was the initial part actually, is that there is 0 fluorinated greenhouse gas in and 0 CO2 equivalent connected compared to SF6 technology. This is here the value of one breaker. This is the dead tank breaker, 145 kV, which is now delivered and in operation in the United States. This is a picture of a 72.5 kV blue GIS. This is a special design for offshore wind towers. Yeah, that's the way it looks like. Here you see the inside actually. What's the components which are in is our current transformers and cables and earthing and disconnecting breakers. The circuit breaker itself is in here, and you see here the nameplate which shows all the different characteristics connected to vacuum and clean air installation. This is the big brother, the 145 kV GIS, and here the aluminum compartment is here just shown, that was taken out to show that there are 3 vacuum interrupters standing in here. On top is a the proven spring type drive actually, which drives that. And here you see the different compartments which are well known from the normal SF6 technology. So the overall view looks identical to today's SF6 technology. 2 topics here. This is a conventional current transformer and the conventional voltage transformers, and there's also a new technology available. Here you see the single line on the right-hand side of that bay with the different compartments. This is completely identical to today's SF6 technology. What's important is that you can substitute the very big current and voltage transformers by a new technology called low power instrument transformers. And the low power instrument transformers integrate into that cast resin bushing, which you always have in here all over the place. You can integrate here the measurement of current and voltage into the cast resin. That makes the whole setup a lot more compact. You see here the space saving indicated by that area by using that so-called low power instrument transformer instead of the conventional power transformers. This is here the outside view on a 145 kV blue GIS with here that LPIT integrated. So this is a cast resin insulator with integrated current and voltage measurement. Yeah, this is cut off the same again with the different nameplates issues here. So as I said, clean air has lower dielectric strength than SF6. So how to compensate that? There are 2 ways to compensate. One is to have a bigger distance between the conductor and the housing, and the second, higher pressure. So we did combine that. So we did increase the pressure from 6 bar to around 8 bar in that blue technology, and we used bigger housings. But what does that mean, bigger housings? I just want to show you how a GIS looked like, which was installed 50 years ago in 68. So it had a bay width of 2 meters and 40. That's quite a big bay width. And the latest SF6 technology now, which is now built today and offered today, has a bay width of 800 millimeter. And how much bigger now is, or wider now is the clean air technology. So the clean air technology is on 1 meter. So we do have a higher size and bay width than today's SF6 technology, but compared to the early days of GIS technology, it's still much smaller. So the way we built here is the size of SF6 10 to 15 years ago. So from our perspective, and also discussions with our customers that's worth doing that, because the man-made gas SF6 is not needed anymore. So let's face it, this gas is just produced to put into power grids and high voltage and medium voltage parts. Here are a few arrangements. This is an H arrangement with the blue technology, which you see here, the single line and this setup. It's very compact. And here now are a few pictures of installations. This is the first 145 kV SF63 substation. So this uses vacuum interrupter technology and clean air insulation. So it's on the upper right-hand side, the live tank circuit breaker, and on the lower left-hand side, it's the current voltage transformer, which is gas insulated, but not with SF6, but with clean air. So that was installed 4 years ago. Here you see the first installation of the 72.5 kV blue GIS in 2017. Here you see that's near shore, very close to Denmark, and it's put here into the base. Actually, it's one bay, which was realized at that time. It's the standard. Meanwhile, as you might know, there is lots of offshore wind generation in Europe done meanwhile, and the big wind parks also cover around 100 wind turbines. And due to the high power which is generated, originally the medium voltage connection from 33 kV was increased to 66 kV to lower the losses. And the next step also in Europe, offshore windshore, will be to double that on 132 kV. So the projects realized in 5 years will have so much wind power generated that the energy is transmitted on the voltage level of 132 kV. But this is the 72.5 kV for GIS. So we do have meanwhile more than 1,000 units contracted and more than 200 in operation. They are very reliable. They must be reliable because you cannot go there easily. It's far away and the weather is quite often rough. So the reliability must be very high, which is. This is a picture of the first 145 kV vacuum interrupter and clean air technology. We call that blue technology. So why is it blue? We call it blue not just for marketing issues. We called it blue because if you buy clean air, the color code of the gas bottle is usually blue. And we took that color code of the gas bottle and we used it to also symbolize that in that gas insulated product, there is only clean air in. So this is an example of Norway, where that first installation was done in 2020. So it's in operation now for 2 years. And actually Norway is, all the new GIS in Norway are realized in that way. Now is a little break, but I want to show you that technology. So all of that technology we just saw is also combined with digital technologies if there is the demand. So the idea is that all different equipment is connected, not only through control and protection as we know it today, but additionally it has sensors to measure certain status, and it sends the data and makes it available to service and to asset management. So that's the thought behind it. And looking on that, how does that look like, for example, for a blue GIS? So in that blue GIS you are now familiar with, there are certain additional components. There is an antenna sending the data. The gas density is the well-known gas density, but the same value is also now available via the antenna. There are auxiliary switches which send the data. There are the cabinet temperatures, and there are also ambient temperature data. So all these sensors are actually well known from high voltage technology, and we use them to give additionally the signals to make them additionally available through an IoT device, which is built in, gives the data into a cloud, and available in a cloud, it can be taken by software applications and used for service and asset management. So just to show what the benefits are, for grid operations, you are able to see the load status of your products. You can see it depending on, for example, on power transformers, you can see if there is an overload reserve capability of the products. You can manage continuous and temporary overload. You actually, if you have bottlenecks in your network, you are able to transmit additional power and generate revenue. And the number of redispatch, which is quite often needed in Germany due to the fact that the renewable has too much power generated, can be optimized. So the number of redispatch can be lowered. For asset management, you have a clear transparency on the lifetime, on the reliability and fault history of the product, of the asset, and you can optimize the life cycle optimization. So do I need a new one? Can I continue running that? So CapEx and operational expenditures optimization can be done. For service and maintenance, you have a reduction of unplanned outages. You see early the status of your products. You have a reduced costs due to the fact that you don't do time-based, but you go into predictive maintenance. You see coming if a failure is available. You have an increased safety because you don't need to go to the equipment to see the status of that. So the status is sent to you through an app. And in case of SF6 topics, you see you have an early indication of leakage before you usually have the alarm, the warning and the alarm. Actually, you see that earlier. And if you apply that on the oil topic, you also see the oil leakages early. So those are the benefits of that technology. And actually, that the idea behind is that you merge the now the cursor is not moving, now it's moving. That you merge the real world here. You see here a GIS and a power transformer. You merge the real world with the digital world. So behind that, in the cloud available are the digital twins of your products, and you compare actually the real values with the measured with the digital values here, and you get benefit out of that. Here's shown, the idea is shown here. So on the left-hand side, you see the hardware. The hardware is connected with the cloud, and it goes into a SenseGear platform. And you have a basic technology on the left-hand side. On the right-hand side, you can have advanced functions made available in your apps, actually, and through additional sensors. That's the philosophy behind it. The problem with sensors is always that they have a lower reliability than the high voltage equipment itself. That's very often the case, and also in automotive and so on. So we did test all the sensors and the whole systems very thoroughly with EMC testing, with mechanical endurance tests, with high voltage, high power testings, which you see here in our testing departments. So the whole system, which we call SenseFormer, SenseGear, was tested very thoroughly, also on lowest temperature, on highest temperature, so to achieve the highest possible reliability of the whole sensor system and connectivity system. Giving you now the example, how does it work in daily life? We start developing a product on the lower left-hand side in our design departments, so it's just virtual, there's no reality yet. Then we start simulation with that product, actually on the different topics, mechanical simulations, electrical, temperature rise, and so on. Once this is optimized, we actually do design and buy the parts, and we do assemble them, and we do test. the parts, and we always compare with our simulation and the testing results and optimize that. And once this is done, everything is put together into the type tested and put into real optimization. And once you have that in real optimization and you have the digital twin, it's possible to have a closer look in operation what's happening in my product and to compare it with the simulation models we have. So we can see the future of the behavior with the experience done with the development. That's the thought behind it. One example here, this is a blue GIS on the lower right-hand side, and you have a clear indication how warm it is. You measure that. You have a simulation, a thermal model behind it, comparing that, and out of that you can measure on one part the temperature, and you know the temperature on the different other parts. And that's the thinking behind it. So this is the newest technology with a digital twin technology, which is offered if requested, which is offered additionally. Just to give some examples where that has been done. So a so-called SenseFormer, this is a power transformer with sensor technology realized here in the mobile substation. This is in China. We do have that integrated in an Hvdc interconnector between Australia and Tasmania. So it measures here the load actually, and it has overload capabilities in case more power has to be transmitted between the island or Australia and Tasmania. You have that for arc suppression coils. We do have it installed here in Europe quite often, meanwhile, for live tank circuit breakers, also for instrument transformers, for gas insulated switchgear, and also the first substations which combine all the technologies, the blue technology and the sense technology. Here you see here an example. This will be inaugurated at the end of this year. So now looking further, there is just giving you the example. There is that substation here, for example, which combines the so-called digital parts with the clean air parts, and this is done in southern Germany, and you can access also pictures and movies from that technology, and also from the operators, from their first impressions. You can have that on the internet page, and the link is done here. And Mings, is it possible that you can play that video, which is shown here? It's from Norway.
Yes, let's go.
Perfect. So this is available.
About the environment and people's health. Less global warming potential is not enough. It has to be.
Mings, I can hear the audio, but don't see the video.
The cruise ships and harbor was using their own diesel-powered generation. So we want to make Bergen electrified, pollution-free, with green power and blue switchgear. Developing a clean air product, we start to do something instead of talking. We are moving fast. Our goal is to reduce our emissions to zero. Clean air from Siemens Energy is a safe choice today. Zero F-gases through our clean air and vacuum technology. It has zero impact on climate or environment. It's a huge improvement. The blue portfolio and this solution is a game changer. Hopefully other businesses will make the same kind of improvement. Every day we work to get day zero for more customers all over the world.
Thank you, Mings. For me, it worked well. I hope everybody saw that. Okay, so let's continue. So this was an example from Norway. It's a harbor in Norway which installed the first blue GIS for 145, and since then, which is 4 years ago, Norway is not buying SF6 anymore for that voltage level. So there are certain countries in Europe which already changed their technology for the future. So let's continue. You see more examples. If you go on the homepage, you see more example on the lower right-hand side. This is southern Germany, and the lower right-hand side also combines the blue technology with the sense technology. With the low power instrument transformers, you see examples there from, actually it's still in construction. You see the latest movies there, how it looks like, and the statements of the operators, what was driving them to install that. Now I try to continue. Now it's working. So just to give an overlook where we stand, there are almost 2,000 units ordered and more than 700 units in operation. On the upper left-hand side, the live tank technology, 72.5, the GIS technology, the dead tank technology on the lower left-hand side, the 145 live tank and instrument transformers, which are available up to 420 kV, which is in Europe the highest voltage level we do have. The blue GIS on the lower right-hand side, you see a picture of a future GIS that was a former, one of the biggest AIS substations in Germany here. You see the whole green area, and that will be transformed in operation into a GIS. And you have those two GIS buildings here, and they are connected with so-called gas-insulated bus ducts. And those bus ducts actually also are realized in that blue technology, greenhouse gas-free technology. So you see that lots of customers in Europe and North America decided to go that way. And now we are looking forward also for Africa and other parts of the world to be convinced and to do the first steps towards that direction. You see that there are lots of grid operators globally going that way, and the experiences are, the feedback is it's simpler. The buildings, in case of GIS, the buildings get simpler. Actually, you don't need heating anymore or ventilation or whatever. Installation commissioning is comparable to today's technology. The gas handling is much easier. It's simpler and shorter for installation, but also for service, and also especially then for taking that out of operation. It works perfectly. I mean, we completely tested it as we test every product, SF6 or non-SF6. So it's testing wise on every tests are passed. Actually, it has the highest level, like which is known from SF6. The difference is that we don't have 50 years of experience of high voltage SF6 technology, but actually we have a high number of installations meanwhile. Yes, and especially some countries like in Northern Europe or also Germany, the end customers are also looking on the activities of their utility. And as I see it from the examples in the beginning, this is also very transparent in the operators, Eskom, for example, or Cape Town. So what are the next steps? You see here on the left-hand side, the products we just explained. On the right-hand side, there is the 420 technology with the gas-insulated bus ducts we just showed, and on the lower right-hand side, the instrument transformers. Looking on the development of installations, you see here on the left-hand side, the global installations in different voltage levels. So you see the forecast for this year is 1,400 installations actually. And on the right-hand side, you see the same numbers split into instrument transformers, GIS, and circuit breakers actually. So there is a quite steep ramp up of that technology. And looking forward now, let's have a look. I mean, 145 kV is still, it's an important voltage level, but we have to realize that up to 420 and 550 kV, we are aware of that. How is that done? On the left-hand side, you do see the vacuum interrupters for, here on the right, on that side is the 170 kV 50 Ka vacuum interrupter, and on the left-hand side is the 245 kV 63 Ka. So that was presented in Paris in 2018. So this is a development. Here you see in the middle, you see the 170 kV GIS for 50 Ka. This is a special Korean design. On the upper right-hand side, you see this is a simulation view on a dead tank breaker with 2 vacuum interrupter units here for 550 kV. And on the lower right-hand side, you see our test fields here, where we do have the first, testing on double breaking. So we take the 245 kV vacuum interrupter and put them in series here and as a double break, and we realize circuit breakers up to 550 kV and 63 Ka. That's the way forward. Now looking on the timeline, 2022, you see here, I mean, the 145 kV technology is fully available, and the up to 420 fully available for instrument transformers and for that so-called bus ducts. And the next steps will now be 245, 420, and 550. So we do realize GIS, live tank breakers, and dead tank breakers over the next years. So that will take the next years to do so, but it will make that technology available, vacuum interruption and clean air technology, up to 550 kV within that decade. A different aspect on that is what is happening on the regulation side and what is needed on the specification side and evaluation side. Looking on the regulation side, you see that the United Nations Sustainable Development Goals are followed by lots of countries and companies globally and individual persons regarding the climate agreement. Those are just a few examples what is happening in the United States, in Europe and China. And you see that there are lots of activities and commitments and laws meanwhile. For example, in the United States to have 100% clean electricity in 2035, which is not that far anymore, and in 2050 a net zero greenhouse gas pollution. Europe aims to become the first climate neutral continent, and China wants to peak their CO2 emissions in 2030 and be carbon neutral in 2060. Below that, you see lots of different activities, regulations, and laws in different parts of the world. Just want to give some examples. Here, there is a so-called Climate Council, which gives a report out every 4 or 5 years, and which confirmed that SF6 is not only the strongest greenhouse gas, but even higher than thought before, and that the F gases C4 are also stated as climate gas, greenhouse gas meanwhile. You see that here. Second topic is on F gases and greenhouse gases. There are activities in Europe and California. I will come to that. And on the toxicity side and environmental side, there are also activities on chemicals and so-called PFAS, pair and polyfluoroalkyl substances, including the F gases. There are activities in Europe and in the United States. And there are the first grid operators who stated they will not buy equipment with a global warming potential above 1. And for example, National Grid in UK wants to buy no SF6 from 2026 on. And additionally, they want to replace all the equipment with SF6 by 2050. So those were the first statements, I would say, from grid operators. Just having a closer look on California in this case, you see this is a regulation in California which has become a law, and you see that for medium voltage this will be phased out over the next years, and for high voltage, for example, the first phase out date for SF6 will be January 1st, 2025, which is less than a bit more than 2 years, 2.5 years ago. They will not SF6 is not allowed to be installed anymore. Looking on Europe, there is a draft of a regulation out, and the draft states here the following: medium voltage phase out and prohibition in 2026 and 2030, and for high voltage in 2028 and 2031, depending on the voltage level. So those are the regulations regulations on the greenhouse gas side. The second topic is on the health and safety side. There are risks connected with certain F gases. There are health risks connected, and that's why in Europe and in the United States, those gases were listed on a so-called registry of restriction in July last year. And for example, in Europe, this is planned to be prohibited in 2025. This is only allowed to be used if it's of essential use for society. That's the wording. And from our perspective, in power grids, those gases are not required because there are better alternatives and more healthy alternatives. That's why we do not follow that way, but we follow the way of clean air and vacuum interruption. Here you see some statements which are publicly available regarding that. The restriction process is running in Europe. There is a restriction process, or several there in the US, which prohibits that. There are some states in the US which already prohibited the use of those gases, PFAS gases. And now the question is a bit for our daily life and power grids, what does that mean? So that means actually that specifications have to be adjusted because today's specification for SF6 will not lead to the sustainable technology which is needed for the future. So there are 4 parts that have to be considered. There must be health, safety, and environmental criteria considered, sustainability. There must be technology criteria considered as known before. There must be operational and maintenance parts considered, and there must be investment parts considered, which is more than just the price, the investment. It's also the operational costs, and it's especially also the cost and end-of-life cost once it's in the environment. So the evaluation, the specification itself and the evaluation must be widened and adapted to the new requirements of sustainable products. This is an example of a list. We talked to lots of customers how they work, and so there is a list of possible requirements which you can pick. You can pick the requirements and to give them a weight, and then do your evaluation connected with that. This is the idea behind it. So there are, depending on the different utilities, there are different values and evaluations. Here we show some specification and evaluation. Maybe you cannot read it, but I can tell you that for example here, this is from Austria. They actually split between price and technology, 70-30. This is from Germany. This is 40% is total cost of ownership, 5% is a contract, 40% is technology, and 15% is project management. This is from Switzerland, actually also a split on price, on technology, on references and service. This is from also different parts of Europe, whereas also a different split. So there are lots of examples already available, how different grid operators specify and value the offers actually. And sometimes the presentation is stuck. So lots of them in Netherlands and Germany, they are also specifying a global warming potential of smaller than 1 or equals 1. This is the railway in Europe, which is completely electrified, and actually by having a complete CO2 neutral railway system, actually also need a complete CO2 neutral electrical grid behind it. So those are different examples here of different. TenneT is actually the biggest, one of the biggest grid operators in Europe, who also specify global warming potential smaller than 1, and so on. And you see on the right-hand side, this is an example from Belgium, also with a different split of values and specifications. So let's conclude. There are certain aspects to be considered: environment, health and safety, regulation, costs, and technical capabilities. The clean air and vacuum technology has very strong performance on all of those aspects. There is 0 greenhouse gas, 0 degrading effects, 0 toxicity. Cost risks due to regulations are low. Maintenance of the vacuum interrupter is 0. Life cycle and end of life costs are very low, and it has also very strong capabilities. So looking on the acceptance of the different of our employees, of society, of shareholders, it has a very good high acceptance globally, and that means actually that this technology has a global warming potential of 0. It has 0 pollution, 0 toxicity. Regarding regulations, it's the safest available. It's very reliable technology and has the lowest lifetime cost. Simple gas handling, no recovery and recycling needed. And what's very important, it's very easy to buy that gas because there are multiple gas suppliers available, which is different to the F-gases because this is a monopoly gas supplier globally. There's only one supplier for the so-called F-gases. So it's an open technology, I would call it, an open source technology. And I'm looking forward, yes, to your questions first of all. And I hope that this is an offering which helps you from power grid operation side to realize sustainable grids of the future. Thank you very much.
Thank you, Dr. Belbig. Thank you for your presentation. I think it was well packed and well informed. I actually enjoyed the link between sustainability and the technical discussion. It wasn't just a sustainability discussion, but it was more informative and more technical. And I'm sure the audience or the members will also agree with me with regards your presentation. We've got few questions that are coming in. Maybe the first one, I can just give you the first one. We can take them one by one. Maybe if it's going to be easier for you. How is SF6 gas destroyed or broken down into safe products? That's one question coming from France. Maybe we can give you an opportunity to respond to this one.
Yeah, that's a very good question. Let's face it. Globally, there is so much demand for high voltage products and SF6 products that actually up to now there was no need to destroy any SF6. So what is done usually, it's the old SF6 is brought back to the manufacturer of SF6. They do actually kind of filter and renew it, and they sell it again. So up to now, the last 50 years, there was no need to do that. But looking on the physics, on the chemistry, it's possible to burn that, but actually there is today no big industrial installation which can be done. This is still done on a laboratory site. So it can be burned, but actually it has not been done yet, since the SF6 amount globally is increasing year over year.
Thank you. And also, I mean, with the recommendation and the information from your presentation, so it's clear that it's another solution that as engineers we need to provide some answers, because if we're saying SF6 is no longer a solution, then the question is, what do we do with all these switch gears that are currently installed if they're not really taking us to net zero? That's where we want to be. Yeah, now agree. And another question there, what is happening about the bus insulation? Is that also air in future? And what about the size?
Which insulation? I did not understand properly.
Bus insulation.
Bus bar. So the bus bars in SF6, like you see here, those are the bus bars of SF6. They are also today filled with SF6, and they are filled also already today, in this case here, with clean air. So the whole, this is one bay of GIS which you see here, the complete substation, complete GIS switchgear. It's all filled. All parts are filled with clean air, and switched is with vacuum interrupter technology. And at least in high voltage, there's usually the gas insulation. In medium voltage, there are also solid insulations, but in high voltage, the standard insulation type for bus bars is also SF6 today, and will be completely substituted by clean air.
Great, sorry, I was muted. Great, thanks. Thanks, Dr. Albig. And then there's another question also, does blue GIS mean air insulation? Is it the same thing when we talk of blue GIS?
It's a bit confusing, I must admit, because there are so many words used, and they are almost the same, or there is a so-called wording of dry air. So Asian companies call it dry air. We call it clean air, which is actually the same. And at the end, it's an air insulation. The difference to the normal air insulation is that it's compressed air. So the wording compressed air is also synonym. So compressed air, clean air, dry air is mainly identical. And it's an air insulation with compressed air.
No, great. Yeah, I think I'm sure there's few more questions, and we've flight your email address, and I'm pretty sure you'll welcome more information or questions if there's any more questions coming from the audience. But these are the few questions that we've received, and I would like to really concur with your closing remarks. I think sustainability, especially more sustainable development, is our responsibility. And the development of the future is in our hands. So what we do with the engineering design, our specification, I like the technical specification focus as well from the UN space. I think it's something that's quite interesting, especially with regards to the sustainable development discussions and the sustainable developmental goals. So it is really the future of our next generation is in our hands. So what we do with the design and the engineering solution will determine what future they will have, and are really connected to quite a number of material that you've presented this afternoon. And once again, thank you so much, Dr. Belgen, and thank you to the audience. And I would like now to hand back to Ms. Afrobus for concluding remarks. Thank you.
Thank you very much, Shepherd. Dr. Helbig, thank you very much for availing yourself for giving this very informative presentation. We really appreciate it. To the attendees, I was just struck with a load shedding stage 6. So that's why I dropped off suddenly. So from 4 p.m. this afternoon, South African time, we said there was stage 6 until 10 p.m. tonight. So please stay safe, and hopefully you have the means of staying warm in this chilly South Africa. But thank you for joining us. Please go to the SAIEE website and register to attend the next KZN Centre's webinar. You would find the link in the chat box. Please register for that. That will take place on the 12th of July at 3 p.m. See you then. Thank you and good day.
Thank you very much.
Thank you. Goodbye.
Bye.
Bye.